Croeso nôl, welcome back. This is lesson 2, year 11 physics. It's your work and energy booklet, the third booklet. And end of lesson 1, we finished page 10. So if you can now turn over, please, to page 11 and just write the title at the top. Lesson 2, kinetic energy and gravitational potential energy and elastic energy. So we're looking at 3 different types of energy. Let's put a comma in there instead of 2 hands to be grammatically correct. There we go. Kinetic energy, gravitational potential energy, and elastic energy. And write the date down. Quick look then at the learning objectives of this lesson. And as you can see, we're going to be completing pages 11 to 15 in your booklet. Here we go. And this reads, the fact we'll be learning here, the fact that an object can possess energy because of its motion, called kinetic energy, and its position, called gravitational potential energy, and deformation, elastic energy. Deformation means when something changes its shape. I just want to do a little bit on elastic energy before we go any further. So this is elastic potential energy. This is a catapult, and as you know, the way a catapult works, similar to a bow and arrow, is that you put an object in here, you pull back the elastic, and when you leave it go, of course, then you get this movement of the object that's in the catapult, because it's a transfer of energy. The stored elastic potential energy in the catapult is transferred into kinetic energy in the object that's been projected forwards. So that's just one example of elastic potential energy. Thinking back to the last lesson, when we used this equation, W equals F times D, you can see here we could work out the amount of energy in here, force times distance. This is the force needed to pull back that elastic. Let's say it's 20 newtons. And the distance D, let's make it nice and easy for me, 0.1 meters, so 10 centimeters, and then using that equation, be 20 times 0.1 would be 2 joules of energy. Then that 2 joules of energy would be transferred into 2 joules of kinetic energy when the catapult is let go. But you'll be concentrating mainly on the other 2 types of energy today, which is kinetic and potential or gravitational potential energy. As it says on the left hand side here, we'll be looking at various contexts, situations. For example, an aeroplane, a falling object, a stretched rubber band, and catapult. Well, we just looked at that one. Then underneath here you can see these are the 2 equations that are going to be used today. For kinetic energy equals half times mass times velocity squared, and potential energy is mass times gravitational field strength times change in height. But importantly, and I'll write it down here. This work is for higher tier only, because you can see, if I rub this off again, you can see that that text's in bold. So whenever you see the text in bold on the spec, it means higher tier. Before we go any further, let's go back to a law that you've already learnt in school. The law of conservation of energy. That means energy can't be created or can't be destroyed. That's perhaps difficult to appreciate at first, because let's say you switch on a light bulb. You might think, oh, you create light energy. No. What you're doing is transferring electrical energy into light energy and some heat energy. There's a difference. And you're not destroying the electrical energy. You're transferring the electrical energy. So when an object, so if we look at this example here, a ball, and so look at this ball being dropped here. When a ball falls towards the ground, its gravitational potential energy decreases and it's transferred to kinetic energy. So if we take this ball here, I colour in blue, as it's falling towards the ground and goes to this point here in red, it's lost gravitational potential energy because it's closer to the ground, but it's gained kinetic energy. It's getting faster. So, however, for everyday situations, friction and air resistance tend to act on a moving object. So that is why, if you look at the bounce of this ball, if I get a ruler and show the height of this bounce and compare it to this bounce and this bounce, you can see that the ball is bouncing a little bit less each time and will, as we know, eventually stop bouncing and remain stationary or at rest on the floor. And the reason for this is because energy is lost. Energy is lost in two different ways. It's lost due to the ball, as it goes through the air, it's rubbing up against air particles. So as this ball is moving down here, it's rubbing up against tiny little air particles. And we've already learnt that would be called air resistance. And that would heat up the ball slightly. But also, here, the ball would actually go out the shape for a fraction of a second. You could see that in a slow-mo video capture, and the kinetic energy then is transferred into elastic energy, just like a spring or an elastic band, and then it would return to its normal shape and go up. But that squashing and stretching effect will result in some heat being produced. So you lose energy from, let's call it point 1 to point 2. And the reason we've lost energy between point 1 and point 2 is due to this air resistance and due to some of the heat being produced here. If you've ever played squash before, you've got to warm up the squash ball, you've got to heat it up, and you've got to hit it against the wall many times so it bounces well. And so that heating effect means you've got to put some energy into the ball. If we look at point 1 and point 2, well, there's less potential energy in point 1 because it's closer to the ground. We call that gravitational potential energy. And you can pause the video and read this paragraph to reinforce the point. Something else it has mentioned here, look, is that friction and air resistance tend to act on moving objects which change some of the energy into heat and sound. I forgot to mention sound. Of course, when you've got something, a ball landing on the floor, then you're going to have that sound energy produced as well. This is why a bouncing ball can never bounce back to the same height. Some of its energy changes to heat and sound, mainly each time it strikes the floor, but also because of this air resistance. Okay. Let's make sense of that. So think of the tennis ball. As it's falling towards the ground, it's losing potential energy and it's gaining kinetic energy because it's moving more quickly. But also, due to the air resistance, there's a bit of work done as well, due to that force of air resistance acting against the ball. If you throw, and when that tennis ball is moving up, so let's see that tennis ball again, on its way up this way, then it's going to be getting slower. So it's losing kinetic energy, it's gaining potential energy, but again, it's acting against air resistance. So again, pause the video, read the paragraph underneath to help you make more sense. Because really, if you understand this paragraph underneath and what I've just talked about, the rest of the lesson, certainly for foundation tier, it's going to make sense. For higher tier, we have to be able to carry out calculations. They make an important point on that first paragraph, and it says, in an exam question, it will tell you whether air resistance and friction can be ignored. If it says air resistance and friction can be ignored, what you do is forget about that work done. So that would mean simply that potential energy lost is kinetic energy gained when the ball is falling down towards the ground, or that kinetic energy lost equals potential energy gained when the ball is bouncing back up. So back to page 11, it's telling us here, so we're looking at the context of rugby again. When rugby players run with the ball, the chemical energy from their food, we learned this before, transfers to kinetic energy in the muscles. The moving muscles move the player. We calculate the kinetic energy of a moving object using the equation. You'll notice Mr. Ruddy has put this H here. That H stands for higher tier. That's reminding us that foundation tier pupils won't need to do these calculations. Let's look at this first question there. You can see Wales winger George North can run with a rugby ball with a mean velocity of about 10 meters per second. That's quick. George has a mass of 109 kilograms. That's big. When running at 10 meters per second, what is George's kinetic energy? So, as I'm sure you know, here's George North, been supported by Alan Wynne-Jones, Justin Tipuric, Gethin Jenkins. Ooh, and that looks, I think that's Dan Bigger in the background. I think it's again from World Cup. Looks like possibly England fullback Mike Brown there with a despairing tackle. It looks as though he's looking for a despairing tackle. Anyway, let's calculate George's kinetic energy. That's what we've been asked to do. Remember, equation, number, answer, units. If you do those 4 things, then you'll be fine. This is more of a complicated equation than usual because you've got to square the velocity or speed, but nothing to be concerned about. So half, where's his mass? Remember, underline or highlight the important bits of information, which are almost always the numbers. There's the height and there's the velocity. I meant to say mass. I think I just said height. Mass and velocity or speed. 109, 10, let's put those numbers into a calculator. $5,450 joules. Please remember to include the unit for joules, and if you're marking that, 1 mark for the equation, 1 mark for the right numbers, 1 mark for the right answer, and 1 mark for the correct units. Next question. You can see the players identified there. It's asking you, calculate the maximum kinetic energy of each player, showing your workings. The information it gives you is that Alan Wynne-Jones has got a mass of 118, Tipperick lighter at 19 kilograms, and George North is 10 kilograms heavier than Tipperick. So a little bit of numerical thinking to do here. The player speed. Now, I think it's fair to say that George North would be the quickest. Then it would be Justin Tipperick, who was no slouch himself, 10.3 meters per second, and Alan Wynne-Jones bringing up the rear there with 9.2 meters per second. So I've shown you how to calculate the kinetic energy there for George North when he's travelling at 10 meters per second. This time he's travelling at this different speed here, 11.1. What I will do though, just to help you, because I'm going to give you this as one for you to do. Alan Wynne-Jones, we know, has got a mass of 118 kilograms, so I'll help you work out the masses and then you can do the rest. And if you don't know how to do it, rewind the video and just watch how I worked out the kinetic energy in question 1 for George North at the different speed. Right, Tipperick is 19 kilograms lighter. than Alan Wynne-Jones. So he's going to be, that's going to be 99 kilograms. And George North is 10 kilograms heavier than Tipperick, 109. Let's just check. Yeah, it's the same mass there, look, as 109 kilograms as is shown there. Okay, so pause the video now then, please, and answer question 2. You need three answers. One for Alan Wynne-Jones, one for Justin Tipperick, and one for George North. If you move on to page 12 now, it's another question for higher tier pupils, whereby it's asking you to calculate the initial kinetic energy of the rugby ball after Dan Biggers transferred his kinetic energy into it. What you need to know then, of course, is the mass of the ball and the initial velocity of the ball, 24.5. That's one for you to do. Pause the video and complete that, please. Underneath that, you see the introduction of the term gravitational potential energy. And again, we'll put it in the context of kicking a rugby ball. So Wales fly half and Dan Bigger kicks at goal. When he kicks a rugby ball, he's transferring kinetic energy from his foot into kinetic energy of the ball, because the ball is moving. As the ball gains height, some of the kinetic energy is transferred into gravitational potential energy. If the ball was kicked vertically upwards, as with a hanging up and under, that's where the ball goes straight up and straight back down. Eventually all the kinetic energy of the ball would be transferred to gravitational potential energy. Now, if we look at the up and under, well, if it was purely up and under, the ball would go up and come straight back down. Showing it here slightly, there's a slight movement up and down. Okay. With distance kicks, only a proportion of the kinetic energy is transferred to the gravitational potential energy, as some of the kinetic energy is used in kicking the ball forward. So that's this one here. And it's telling us how to calculate the gravitational potential energy by using this new equation here. Again, it looks a bit more complicated than what we've used previously, but believe me, you won't have any problems with it. You're just multiplying three numbers together. Underneath, it's the same equation, but just using the symbols for mass, gravity, and change in height. Calculate the gravitational potential energy of a 0.44 kilogram ball. So again, highlight the important parts. Kicked vertically upwards 20 meters. You know, again, equation, number, answer units. If you do that, you can't go far wrong. So I'm just going to use the symbols, as you can see just at the top of the screen at the moment. MGH, M times G times H. The mass then is 0.44. You can see that's highlighted above. G, highlighted above, is 10. It's gravitational field strength, and it's kicked to a height of 20 meters. You can see those numbers now have been put in a calculator on the right hand side, and the answer is 88 joules. So that's the gravitational potential energy that's gained by the rugby ball. Turn on please to page 13. Question 2 is asking what is meant by gravitational potential energy. Well, that's the energy gained when an object moves upwards against gravity. Upwards is going to be against gravity. So it's moving away really from the center of the earth. If this is the earth, gravity acts in towards the center of the earth. Remember, it tries to pull everything, wherever you are in the world, tries to pull everything in. So if you've got an object, I'll represent that with this red dot here. If you move in this way, away from the center of Earth, then you're gaining gravitational potential energy. Question 3. Apart from gravitational field strength, what 2 other factors dictate the gravitational potential energy of a rugby ball? To help you answer that, just remember this equation. So it's saying, apart from gravitational field strength, what are the other 2 factors that affect or dictate the gravitational potential energy of a rugby ball? Well, that's going to be mass and height gained. Right, so you can answer that in your own words underneath. Question 4. Now, by the way, if we look at what I should have done, this is for foundation and higher, of course, as is question 3. Now, question 4, this is where it's higher tier only, because there's going to be an element of calculating potential energy again. Let's just pause the video and have a read through that yourselves. Now this is for you to do, and if you're unsure, go back in the video, look at how I showed you to answer question 1, because it's exactly the same thing. The only difference is that we're changing the mass and possibly the height. And for the size, you've got the size 3 ball, size 4 ball, different mass, size 5 ball, different mass. Gravitational field strength for all 3 is obviously going to be the same. It's not as if Dan Bigger is going to kick one ball on Earth, another on Mars, and another on Jupiter. It's staying the same. Also, he's kicked them all the same height. That takes a bit of skill. 35 meters. Best way to lay out your answer then is to work out the gravitational potential energy gain for the size 3 ball, for the size 4 ball, and for the size 5 ball. So pause the video and do that, please. Okay, now this question, question 5, is a far more challenging question, and I'll go through this with you. And it says, Wales hooker Scott Baldwin. By the way, that doesn't look like, it certainly doesn't look like Scott Baldwin. And I don't think, it's certainly not Wales, and I don't even think it's Ospreys. I know he doesn't play for Ospreys anymore. I think he's gone to an English club, possibly Harlequins. Scott Ball would remember. He is a Welsh hooker, has played for Wales in many caps. You might remember him for going on tour to South Africa and tried to smooth the lion, but unfortunately had his hand bit by the lion. Yeah, highly unfortunate. But anyway, the important thing here is, what are we trying to work out? We're calculating we've been asked to calculate the mass of the ball. And in order to work out the mass of the ball, we're going to have to use this equation. And put in what we do know. Now what we do know is, and we'll highlight it goes from an initial height of 2 meters to 4.2 meters. So the height h there is 2.2 meters. The gravitational field strength is given here. Again, we're on the planet Earth, so it's going to be 10. And we are being asked to work out the mass of the ball. We're also told that the gravitational potential energy gained is 9.9. So we put 9.9 there. Now, from here on in, the physics is done. Now it's the maths. So on the right hand side, 10 times 2.2 is 22. Mass equals 99 divided by 22. I'm just rearranging by dividing both sides by 22, and then you'd need your calculator. (99) divided by 22, and that comes to 4.5 kilograms. I'm pausing there because I'm thinking to myself, oh, that's not a sensible answer. Because I remembered a 4.5 kilogram rugby ball, that would be far too heavy. Because look, up here we got size 5, 0.45 kilograms. I'm thinking, I've made a mistake. So let's go back down. I'm up by a factor of 10. Yeah, G's right, H is right, 2.2. So I'm just going to check that 99 again. Should have put my spectacles on. It's not 99 joules, it's 9.9 joules. Which will change everything by a factor of 10. It wasn't, as some teachers would say, a deliberate mistake. It was a genuine mistake. However, what you need to do with any question like this is ask yourself, does that sound right? Does that answer sound right to you? So what I should have done is 9.9 divided by 22, and that gives you, that's better, 4.5. 0.45, I've done it again, 0.45 kilograms as the answer. What a mistake I did make. Right, now then, if we, okay, next part applies to foundation and higher tier. And it says you could get a 6-mark question in your GCSE exam that asks you to explain the energy changes that occur when an object like a rugby ball is thrown or kicked upwards and comes back down again. Highlight the words and phrases the examiner will be looking for you to use. I'll start off and then I'll leave it for you to finish. So, when Dan Bigger kicks a ball vertically upwards, he applies a force to the ball at the instant of the kick. In doing this, the force moves through a distance. Now, I think it'd probably be looking for the fact that you apply a force to the ball because that's a transfer of energy. Yeah, the force moves through a distance, so that's the work that's done on the ball. And Dan's foot does work on the ball. Yeah, okay, so that's the energy being input. It's transferred. Definitely need to be talking then about how that work done is transferred into kinetic energy from his foot. And some is lost in heat as heat and sound. Because you'll hear the thump of the foot on the ball and there will be some heat generated. That won't be as evident. The ball's kinetic energy then starts to reduce, as it gains height, moving against the pull of gravity and increasing gravitational potential energy. The force of gravity does not, or does work on the ball, I should say. Eventually, the vertical velocity of the ball gets to zero as it reaches the top of the kick. You could almost picture what's happening. The ball's going up, and just before it starts to come back down, that's when it's got its maximum gravitational potential energy. So we're at this point now. It's at the top of the kick, just here. The kinetic energy has all been transferred to gravitational potential energy. Right, so kinetic, change of gravitational potential. As the ball starts to fall back down again, the opposite happens. So we say gravitational potential is transferred to kinetic. However, at any one time, at any height, the total energy of the ball is constant. That means if you add up the kinetic and the potential energy that are shown underneath here, it's always going to be the same. Energy is not created or destroyed. It's transferred from one form to another. So let's look at this then. Work done. So I'd like you to do that. I'd like you to just annotate the paragraph above with the different numbers from here. So this is picture one. Picture one, foot exerts force on a ball, moving ball and doing work. So that would be right at the start here. Let's go back to it. It is, and I'm going to put in number one on that line. Number one there, force the ball. Doing this, the force moves through a distance. That's picture one. Transferring kinetic energy from the ball into kinetic energy. So I'd say up to there, picture one. And I want you to do the same then for 2, 3 and 4. Assume gravitational potential energy is zero at the point of kicking. Okay. So what we can say is then the total energy that's been put into the ball is 15.4 joules. And at the point that it leaves his foot, it's all 15.4 joules and zero gravitational potential energy. Here, kinetic energy has been reduced by 75%. Okay, and I have to work out what 75% of 15.4 is. And the easiest way to do that is just put in 15.4 and multiply by 0.75. That's 11.55. So what we've got then is 11.55 kinetic energy. We know that the total energy remains at 15.4. Just had a quick peek because I forgot what it was. And then to work out the gravitational potential energy, you need to take away, it's just a bit of maths now, isn't it? You need to take away that 11.55. So I'm doing 15.4, take away 11.55, 3.85 joules. I'll put that in red. 3.85 joules. Okay. Now when it's at the top, it's got zero kinetic energy. So zero kinetic energy, 15.4 is the total energy, and you've got 15.4 there. At any time, the amount of energy the ball possesses remains constant. Well, can you make sure though you do go back to here and you label each line, this is going to be 2, 2, just so you show when you understand how this paragraph at the top there links to these pictures. Well, that's the end of lesson 2. Make sure please that you complete the assessments that go along with this video in your study zone, and you complete all parts of this lesson. See you next time. Bye.